Okay, anyway, welcome to lecture 15. So let's continue from from what we were looking at last time. So I think last time we wrote down the following, right? So let me just start. This is of course a new section. So we've understood the problem in the cylinder, and now we want to reconsider the questions again with respect to a general operator on a manifold with compact boundary, right? So that's our goal. So the general problem. So last time, so I'll write this lemma out again because it should really be here. So last time, we wrote down the following lemma, right? So throughout let R prime be the constant in the operator reduction lemma. Okay, so that's the constant from the operator reduction lemma that we had from before. So last time we saw that. So what did we show last time? So last time we saw a lemma that told us that okay, so let me just find it here so I can write it precisely. Okay, so it told us that if we have U in so how did we write it actually? Did we write it for, yes. Yes. So this was the corollary from last time, yes. So that's right. So let me just recall it. So I think we wrote for smooth functions on the cylinder up to R prime. So if U is in the cylinder up to R prime in E, yes, there's a bar, with support of U contained in a ZR prime. Okay, so I should say there exists a constant, right? So the constant, there exists a constant C1, finite constant such that for all, so it's for all U in this cylinder with support contained, so the support doesn't touch the R0, the fake cylinder. So here we're invoking our results from before with a parameter with rho equal to R0. So the support of U is contained in the cylinder. So there exists a constant such that for all U with support we have the following bound. So we have U in the H1 norm on Z R prime is controlled now by C1 against dt plus a U squared. Okay, so this is L2 on the cylinder. So this is what we had last time. Chi plus A. Aha, sorry, you're right. Yes, sorry, there's a condition missing. This is of course not true in general, right? Otherwise we would we would always have that the maximal domain of the operator is contained in H1. So we support U and with chi plus of A of U at 0 is 0, then this holds. Summoned norm of U. Sorry, yes, of course. Yes. So the constant here is not in U, right? That's what I want to, yes. So yeah, sorry about that. These technical things are easy to forget. Okay. So this is something that we have to really keep in mind. So this is a very important result that we're going to use today. So, so to begin, to continue our discussion with the general problem, so what we want to do is, starting with the general operator, we want to reduce the general problem to just a question about the cylinder ZR, right? Because the cylinder is diffeomorphic geometrically, in fact, to a neighborhood U of the boundary, as we recall, right? So that was, we had two things. We had before the geometric reduction lemma, and we also had the operator reduction lemma. Okay. Well, okay, so what it means when I say diffeomorphic geometrically is, remember, the collar neighborhood theorem says that a collar neighborhood of the boundary is comparable to a neighborhood U, but the geometric result tells us it's more, right? It gives us information on how to actually control things, geometric quantities in that collar neighborhood. Remember, it tells us that the measure looks a certain way. The given the vector field T, we actually obtain the neighborhood with respect to the vector field T, and so on and so forth. So it's not just a diffeomorphism, it's a diffeomorphism that satisfies a whole lot of other geometric conditions. Okay, so so let me just first note a very important a technical result. So this is a general result. So let T and S be operators on a Banach space. Well, they should be closable operators, right? Closable operators on a Banach space B. And suppose there exists a constant, there exists a constant in 0, 1, and D a finite constant such that T of U is less than or equal to C S U plus D of U. Okay, so maybe D is maybe a bad choice because we already used D for many other things. So let me say C tilde. Okay. Then the claim is, then the domain of the closure of T is equal to the domain of the closure of T plus S as operators, and with the norm equivalence, U in the T norm is comparable to U in the T plus S graph norm. Okay, so it's saying that, so actually this condition is really saying that T is S bounded, right? Because it's bounded somehow in the graph norm of S, But the important thing is that the homogeneous part of the operator, namely the constant that appears against the norm of S of u, is less than 1. That's really the important thing. So in general, you cannot make both constants less than 1. So trying to make the constant c here less than 1 typically means that you have to feed more into the constant c tilde. So so the constant c tilde might be very, very large. In fact, the infimum of all such constants c, such that this is satisfied, is really the S norm, the S bound of t. Okay, but we won't get into that. We'll just leave it at that. So why is this important? So this is important for the following reason, right? So let's now write out, yes? Yes, but that's always true, right? I mean, without the constant c being less than 1, right? Because here it's also saying that, I mean, for this equality to be valid, you need to know that the domain of t is, so the domain of S is contained in the domain of t, right? So I mean, it's implicit in there, yeah. Okay. Sure, yeah, that's fine. They can be called little c and big C. Okay, so lemma. There exists a constant C2 positive such that for all rho now, so this is where we make choices of rho that are between 0 and R prime, and u in C infinity Z rho E. So here the Z rho does not touch the fake boundary, right? So here we are really staying away from the rho end. Actually, is that what I want? Let me see. Sorry, no, I wanted to touch the boundary, but now I'm going to ask with support of u contained in 0 rho. Yeah, this is the right way to write it. Partial m. So for all u with satisfying this, the following estimate holds. D minus D naught in L2 of Z rho is bounded by C2. Now we have a rho here, D naught of U, L2 Z rho bar, plus U, L2 of Z rho bar. Okay, so this is setting things up for what we want eventually. So, how do we prove this? So recall that D minus D naught is equal to what? This is sigma t minus sigma naught. Sigma naught inverse D naught plus sigma t RT, right? So this is from the operator reduction lemma. We have a certain form. Given the adapted operator A, we get a D naught, and then from that we have some remainder terms, and we can compute this. Okay. So since t maps to sigma t smoothly, since this is a smooth map, we have that t minus sigma naught so we have the Lipschitz estimate. So maybe I'll write it on the new line. So we have a Lipschitz estimate, T minus naught V is now, say, bounded by C2 tilde of TV. Okay, whenever T is less than or equal to R prime. Yes? Is it? I don't think so. I'm not sure. But this is, yeah, this is the main theorem, so I hope it isn't. So I yeah. Anyway, so let's just go on with it. So no, this is not the, so okay. So the question is this the exercise from the last sheet? No, it isn't, because for the last sheet, I remember the exercise, and there you're using the you're assuming that A is self-adjoint. Right here, we don't have any assumption on self-adjointness, right? So that's an important distinction. Okay. All right. So because we have that T maps smoothly, we have this following Lipschitz estimate, and so by choosing T less than or equal to rho in particular, we have well, okay, so I should say in particular this holds, in particular this holds for T less than or equal to rho, right? Okay. And so what do we have in particular? We have this acting on V is less than or equal to C tilde rho modulus V. Okay. All right now. So now let's estimate this. So we have T minus naught sigma naught inverse D naught of U. So this in L2 on this cylinder is going to be less than or equal to C2 tilde of rho, and I now have this D naught of U L2 over the cylinder closure. Okay. And now, of course, everything gets absorbed into two, so I'll write C tilde tilde as the second constant, so I'm just absorbing the norm of the sigma naught inverse because it's in this compact cylinder, right? So now this is going to be bounded by D naught of U L2 over the cylinder. Okay. So that's the easy term. So now let's consider the term, so now let's consider the other term, right? So now consider so we need to bound sigma t RT of U squared L2 Z rho bar. So now this is what? So this integral is going to be, in particular, it's going to be, well, bounded by 0 to rho. Okay, so I should maybe take a constant here. So I get a constant from, well, what can I call it? I can call the constant, so I can call the constant C3, say. So now this is going to be 0 to rho RTU squared L2. Now this is the L2 on the boundary dt, right? So this is what the L2 norm looks like. The constant C3 arises from taking the operator norm of the sigma t and taking a soup inside the cylinder. Okay, so what do we have from, so now we apply the operator theoretic lemma from before, right? So we apply the lemma and we get some constant C4 and what, yes? Yes, the U also depends on T. So you mean in here? Yes, sure. But I mean, U also depends on X, right? So, yeah. Yeah, like this. Yes, sure. Yes. I was just omitting it, but yes, certainly the U also depends on T. So now we have from before, so the main thing is now we have an estimate on RT inside the cylinder because we chose the cylinder to be less than R prime. We have this estimate from the operator reduction lemma, right? We have that this can now be controlled in terms of A of U, or A of UT, right, if you like. Squared, and now this is L2 partial M dt. Okay, good. So how does this help us? So this is now going to just be C4 0 to rho. A of, now I'm going to apply this to T of U T squared L2 partial M dt. Okay, so I'm just going to take the constant. Oh, sorry, there's an inhomogeneous term missing here. So there has to be an additional term here. So this is C4 rho of, so we have rho of U squared L2 Z rho, right? So we only have this control on the first term, okay? The rho comes from the fact that, so what was the lemma that we had before? Sorry, I don't have it in front of me here. So, yes, well, okay, sorry. The rho comes from this, right? Because we have that inside the cylinder, RT/UT is controlled by A, U acting on T plus the norm of U, but on the cylinder. But now we're integrating from 0 to rho. So the integral 0 to rho, we can factor out, right? Okay, I see what you're saying. Oh, sorry, I have the rho already here in the estimate. You're right. Sorry, I don't have a rho there. Yes, and in fact, I should really have written less sim here. Yes. Sorry, the numerology is always a bit off. You're right. The rho is already in the integral here because it's the L2 integral in the cylinder. Yes. So okay, so we have now this. Well, I'm keeping the constants here because I'm saying in the theorem, in the lemma, that there exists a constant C2. So that's why I'm keeping the track of the constants. So, you know, if I was writing this in a paper, I would discard this away and just not keep the constants. But I think here it's a good idea to keep the constants so it's really clear that we're not having anything T dependent and so on and so forth. When we have to make an assertion about constants being uniform, it's a good idea at least once to try and track what the constants really are. The point here is that we have a C4, right? And it's independent of the T. Because well, it might depend on the R prime, but it's independent of the rho. That's the main point. But if we have if we have this in the less sim form, then it's harder to see it, right? So let's just keep the constant for the moment. So okay, so what have we really gained from this, right? So this is really where the proof also is different from the self-adjoint version of this lemma, because here we really have to resort to the results that we proved previously in the model problem. So let v of t equals to tu of t, right? So this is what I'm going to put. So then that means that the support now of v is contained in 0 to rho across the boundary, right? In particular, v of 0 equals 0, right? So that means that chi plus of a of v of 0 equals 0. And so, and what else do we have? So we also have that, so here this is where we have the rho coming in, right? So also, so I made a mistake there before in this L2 norm. So also we have that v L2 of z rho is going to be less than or equal to, now we have that this is less than or equal to rho u L2 of z rho. Okay? Good. So so what do we have here? So now we can integrate. So what we have is, from before, we have that dt v squared plus av squared L2. So these are all L2 integrals on the boundary. Dt. So this is, of course, comparable, as we wrote before, to the H1 norm on z rho squared. And we have that this is now bounded how? So from before we have this constant C1 that is independent, right? So we have some constant that's independent. So of course the constant here in the comparability norm of the Sobolev norm and H1 is also independent of well, it's something that just depends. That's dependent on R but independent of the rho, right? So we have here that we get this to be bounded now in terms of dt plus AV from the previous, not the lemma, but the proposition, right? L2 of Z rho bar. Okay, so from previous corollary. Okay, so actually understanding how to do this was a very significant part of actually getting all of this to work for the general order case, because the self-adjoint case, one argues this very differently by expanding out the inner product and explicitly computing things using the self-adjointness. Okay, so what do we have here? So what's dt plus A of V? Yeah. This first comparability, well, A is a elliptic operator, so this allows us to control the H1 norm on each slice, and the dt is a operator that differentiates in all the directions other than the ones that A controls. Yeah, but A is a the main point here is that the A is invertible. So the invertibility means that the zeroth order term is controlled by A itself, right? Invertible means that it's bounded below. And that's why we are constant. So that's a very good question. So one of the big reasons why we are working with operators without kernels is because it just takes a lot more ink to keep writing the lower order term. Right? If we just absorb the lower order term and make the operator invertible, we can always do that, right? Because if the operator has a kernel, then we can move the spectral cut a little bit, you know, to the left of it or to the right of it, and we can draw. We get an admissible cut, and then we subtract the operator, and the amount we've changed the operator is just by a lower order amount, and then that gets absorbed into the operator reduction lemma as the lower order constant. So that's really the fundamental aspect of all of this, is that we are always working with an invertible boundary adapted operator. That's because we can then control Sobolev scales just from the operator itself. Oh, you mean there's a norm here? Yes, you're absolutely right. That I should really write here. Yes, that's true. That's true. Okay. Right. So was that the way that I wrote it? So let me just see what the corollary was. C1. So y is there no constant. So I think the C1 needs to be in both places, right? Yes. I think before when I wrote it, the C1 was in both places. Yes. Anyway, it doesn't matter. We'll see how to absorb all of these constants anyway. So I'll make sure that when I write out the notes, I get all of these constants and everything sorted out. Okay, so dt acting on A, so this is just Tu. So if it's Tu, what do we get? We get, now this is U plus T dt plus AU, right? This is what we get. So that means that 0 to rho of dt plus A of V squared dt is equal to 0 to rho of now u plus t dt plus A of u squared dt. And obviously this is now going to be less than, so what's it going to be less than? It's going to be less than, so I have a t here, so I can I can bound that above by the rho. So now I'm going to get form on the cylinder of this u squared. So of course there might be a constant here. It's a constant that, I mean, 2, right? 2 is a good enough constant for this. So now we get a rho here, dt plus A u squared dt. Now we have L2 over the cylinder. And there's a rho squared, sorry. And now I want to change this to d naught, and that's just again using the boundedness of the sigma naught, right? So this is now going to be 2, some other constant, C5 say, okay, so I'll have C5 rho squared d naught of u squared plus 2u L2 z rho. Okay, so now take, I don't know, let C2 be, yes, be the maximum of all, well, and I'll make this actually C5 squared, constants appearing here. And so what do we get? We get that d minus d naught of u now is going to be less than or equal to, okay, so we put all of this stuff together. So we have lower order term here, we have a lower order term here, and we have a lower order term here, right? So we put all of these lower order terms together, but the important thing is that in front of the d naught term, we get the rho squared, right? So actually, the C5, for the C5, all that really matters is, yeah, so we have to collate the right constants, and then we get something like C2 rho, oh sorry, yeah, d naught of u L2, so this is L2 over this cylinder Z rho bar plus some, now we have some other constant that we cannot control, so call it C3, well, we already had C3, so C2 tilde U L2 Z rho bar. Okay, so that's what we end up with. C2 and C2 tilde. That's true. That's not so good. So, C7. The main point is that here, the C2, so what's really important here is the C2 here, right? That's really the main important thing. That it takes a form like this. Okay. So yes? Yes, because I've absorbed it all into the C7. Right? Yeah, but that's okay. V is just T times U. So just take the norm, turn the T into a rho, and then you can absorb all of those constants into the C7. Yes, that's right. So you can also majorize this all by R prime, right? Where C7 is also chosen appropriately, absorbing required constants, including rho, which is less than R prime. So the thick and thin of it is that, you know, and you can see explicitly in this how this abstract lemma that I showed you really comes about. So in order to get control on what happens on the homogeneous part of this operator domination, we might have to push more and more stuff across to the inhomogeneous part. And that's really what happens, right? We cannot really control the constant C7. That might just blow up and head towards infinity. It's still finite, but it'll be very large if we want to try and make the norm here smaller, right? So what we're really doing in principle here is we're moving away more and more of the inhomogeneous, the lower order term that's present in the operator D naught out, and compensating for that by allowing the norm there to blow up, or the constant there to blow up. Okay, so the most important corollary that comes out of this now. Whenever rho is less than 1 on C2, okay, so we can choose the rho. I mean, that's the beauty of all of this, right? We can choose it to be small enough. We have that dom dc equals dom d naught c, where dc is equal to d, so restricted to now this, okay, so dc and d naught c are the closures of, so maybe I should really move that out of the corollary, right? So yes, let me be a little bit more precise. So let me just move this down and phrase this first. So let d naught c be the closures of d and d naught respectively with domain u in C infinity z rho bar e such that well, because then we have to come up with too much notation, right? I mean, okay, call this CL. Yeah, but the closure of the operator on what domain? You have to specify then the operator on a certain domain, and then you have to specify that operator. You can't just take the closure of any operator because I'm giving this a specific domain, right? So this is the support of U that's going to be contained up to rho cross partial M, right? So it doesn't see one end of the boundary. It's not the maximal operator, right? This is a special operator. So I don't know what to call it. See, yeah. I don't know what good notation it is. There's just too much stuff floating around. CL, yes. Oops. CL. Okay, so we're closing it where one end is not seen, right? It's like choosing a boundary condition on one end, the minimal boundary condition on the one end, because that's a fake boundary anyway, so we don't care. Okay. With estimate DCL of U, U DCL is comparable to U D naught CL. Okay, so immediately this comes out of the lemma that we've just proved. So what do we have? So we have, for this choice of row, we have from the lemma that d minus d naught of u L2 on Z rho is bounded by b d naught of u plus, I don't know what, C7 of u, right? Where b is equal to C2 dot rho, which is less than C2 1 on C2, which is less than 1. And that's the main thing, right? So from abstract result, with t equal to d minus d naught and s equals to d naught, obtain t So actually in the abstract result, I think it was S and T plus S, sorry. The abstract result was phrased a little incorrectly. Sorry about that. So where is it? It was the domain of S closure and T plus S closure. All right. So, okay, so we obtained that S closure, which is equal to D naught CL, and T plus S closure, which is equal to D naught minus D plus D naught closure with respect to this domain that we wrote before, which is precisely equal to D CL. Okay? So the point is that we've at least identified two interesting non-trivial extensions that see the full boundary, the real boundary, not the fake boundary, but the real boundary, whose closures are comparable, right? Because what we... Yes? Well, the S and the T have a certain domain, okay? So I should say, okay, to be totally precise, with domain U in C infinity, Z rho bar, E. I mean, you cannot ever think about unbounded operators as just their action. You have to specify the domain. If the domain changes, the whole operator changes, right? So that's a very important. So let me write with domain D equal to this, support U in support U is the subspace of 0 to rho cross the boundary, and then I'll put D here. Okay, so this is right. So now I think it's okay. All right. So what I wanted to say is that this really allows us to move between maximal domains of the two operators by instituting cutoffs to kill the fake boundary, right? That's really the important aspect of this corollary. So now, in order to proceed, we need to make an additional, very important assumption. Okay, so let us recall the general situation. So we have M is a manifold with boundary. The boundary is compact. And we have this operator, right, that takes us ME to MF. So this is the general situation that we have. So now we need to really, so the point is that the manifold itself may be non-compact. This could be something like an exterior problem that we're looking at, right? So we need to make an additional assumption, right? And here we make this assumption. That the operators D and D perp or D dagger are complete. Oops. By which I mean, i.e., say DOM D what's the, maybe I'll put a little c here, which is U in DOM D such that U support of U compact. and dom C D dagger, which is U in dom D dagger, max, such that support, this is, I'm defining it. These are elements in the domain, in the maximal domain, such that the support is compact. Are dense in dom D and dom D dagger respectively. So completeness means that compactly supported sections are dense. Okay, so if D is complete, then C infinity C of ME is dense in dom D. Okay, so if we have a complete operator, i.e. if compactly supported sections are dense, then that's enough to guarantee that compactly supported smooth sections are dense. Okay. Now, let's prove the main theorem of all of this. Theorem. Let D be a complete, let D, let D be complete, and A an omega bisectorial invertible adapted boundary operator for D. Then H check space of D is equal to the H check space of A D naught. Okay, so this is the theorem that we want and we can prove. Right, so this really shows us that we can discard at least, so it tells us that we can really discard the geometry near the boundary, right? So D and D naught are different. They're not equal on a neighborhood of the boundary. Nevertheless, we can still equate the check spaces of the two operators. Okay, so this is sort of the grand goal that we had in mind for a long time, right? This was question number 3, or desire number 3 that we talked about. So the point here is that, of course, one can argue that here we're still describing things that in a way that it's related in some way intrinsically to D. But the point is that the operator A only depends on D at the principal symbol level, right? The operator A is built out of the principal symbol of D. So it is purely an object on the boundary that determines a model operator D naught in a cylinder. And the claim here is that we can understand the full boundary value problem. So for the full operator D, which might be very complicated, simply from considerations in a cylinder of the model operator on the boundary. So what we did up to this point on the model problem looked like we were looking at something very specific, but actually that scenario contains all of the information that we actually want in order to understand the operator D. Okay, so let's let's prove this. So let U be in DOM D max. Okay, then U equals to 1 minus eta. So my U's and etas are looking the same again. So U and eta plus eta of U, where eta is a smooth, compactly supported function on M, landing us in 0, 1, such that the support of eta is contained in this U row, which is diffeomorphic to 0 to rho cross the boundary, so near the cylinder, with rho chosen as previous. Okay, so you can see also how the
trouble. You were back for a few seconds, Slash, but then you're gone again.
okay, am I back?
Yeah, you are.
Yes, the internet here is, as you see, brilliant. Okay, so sorry, so as I was saying, the row here is chosen as in the the U row is chosen to be diffeomorphic. Okay, so the geometric reduction lemma tells us that we are always diffeomorphic. There is a neighborhood that is diffeomorphic to a cylinder. Now I go into the cylinder and I pull back to come into a cylinder where the row is small enough. Is that clear? Well, I mean, okay, we can, but I think, yeah, all right. Okay, maybe I'll just, and where U is diffeomorphic to some U R, and the U row is defined as the pullback of this or the inverse map of this 0 row cross partial M, right? With phi from the geometric reduction lemma. Okay. So now what? So let's have a look at this. So let U naught be this 1 minus eta of U, and U naught restricted to the boundary now is equal to 0, which means that U naught is in the domain D min. Okay? So that's fine. D min is something that we can constantly, we can always ignore. So now it suffices to consider the support of eta U, right? So, so what do we have here? So, since D is complete, we have that U naught is, or eta of U is equal to the domain of D close, as we wrote before, and because of the choice of row that we made, right? Which is also equal now to the domain of D naught of the closure. Okay, so now we have that U restricted to the boundary is the same as eta of U restricted to the boundary. And therefore, and moreover, we have U restricted to the boundary is now controlled by eta of U. Okay, so this is of course now contained in DOM D naught max, right, on this cylinder. So every extension is contained in D naught max. So this is now controlled in D naught max. But the point is that of course the two norms are equivalent because it's on a smaller domain. So this is eta of U D naught closure, and well, this is actually equal, right? So this is what the norm D naught closure is, and now from this we have that from the previous lemma. What this tells us is this is now D closure, and this is now bounded, and this is now actually equal to eta of U. Well, I don't know why I keep putting these brackets in here. Don't need that. DCL. D max. So this is in the maximal domain. And so what do we have here? So we have that this is now going to be controlled by U plus, now we have D eta acting on U, or well, the symbol, right? So this is really the symbol of D, D eta acting on U, plus D of U. But this is now bounded, right? This action on the symbol is bounded, so this is all now controlled in terms of D max. So what have we shown here? We've shown that U maps to U from DOM D max to H check of A of D naught is bounded. Okay, so that's what we show here. So we're in this eta U is contained in the model problem. We restrict, so this restriction is trivially, so I should say that this restriction now is trivially in H check A of D naught, right? Because we're taking the restriction in this D naught max with respect to D naught max. Okay. So now, yes? Well, I mean, so the domain of DCL is the closure of compactly supported sections that don't see the boundary row. So in order to be in this domain, you need to know that there is an approximating sequence in compactly supported smooth sections. If you didn't have D being complete, it's not really possible to do this. I mean, if you didn't know that there's a sequence of compactly supported smooth sections, how do you know that you're in the closure of this operator? No, it'll be in the maximal domain. Sure, it's in the maximal domain of D. It'll be in D max, but it needs to be in a smaller domain. So I want to know when I cut off, I'm going to end up in the domain of the operator that I'm interested in. And that operator is constructed as a closure of compactly supported maps, that don't see the fake boundary. So then the question is, how do you prove this containment? To prove this containment, you have to take a sequence and then you know that it's Cauchy because of the completeness, and then you know that you're in the domain of this operator. Mm-hmm. Yes. Precisely. Fantastic. Yes, so thanks for that question. That is really the main point here, right? We really need to know that we're in this space that we construct, because we construct it by taking closure over compactly supported smooth things. Okay, so now we've shown that this is bounded, so it tells us at least that that H check of D is contained in H check A of D naught, right? That's what we have so far. But now let E rho be a map from, say, so from C infinity on the boundary into DOM D max defined by yes, but with respect to rho now, right? So I'm going to define E of rho equal of V being equal to eta of E of V, right? So E of V is the extension operator that we considered before. But now I'm going to multiply by the eta because I want it to only be contained in this small cylindrical part. So I shouldn't say DOM D max here. Let me say C infinity of ME, right? Compactly supported with support E. Okay, so let me say that. So we've defined it by this. Note that E rho V restricted to the boundary is equal to just V restricted to just V, in fact, and that the support of E rho of V is contained in this U rho, right, which is diffeomorphic to 0 to rho cross M. Okay? Good. So now what? So now we have that E P of V clearly is in DOM D naught max. Okay, no brainer there. So I shouldn't have written D max here before. So let me just write this first of all, and by the support property, we have that E rho of V is contained is actually contained in DOM D naught CL, which is equal to DOM D naught of D of CL, which is surely contained in DOM D max. Okay, so what? So this shows us, and this is bounded, right? So with EP of V in H check A of D naught, bounded now by, this is, it's not that. So EP of v of d max is equal to so what is it? EP of V in DCL, which is comparable to EPV in D naught CL, and now this is bounded by what we want, right? So this is bounded by V in H check of A of D naught. Okay, so that shows us that, so this gives us that EP is actually a bounded surjection from H check A D naught to DOM D max, bounded surjection. So that implies then that, so what does that imply? So together with previous estimate, we have that U maps to U partial M takes us from DOM D max to H check A of D naught bounded surjection. Okay, so of course we don't need to check anything about the kernels. We already know that, so that tells us that H check of D is equal to H check A of D naught with comparable norms. Precisely, yes. Because here I'm taking the norm in DOM D max. Now the DOM D max norm is the same thing as taking DCL, because my section here doesn't touch. Well, the surjection is because we've already checked that, right? So here we have this map is bounded into H check of A of D naught, and now I've built, so I've said now for every element in H check A of D naught, I can produce an element in DOM D max such that the restriction is itself.
Yeah.
You mean here, sorry, here, yes, sorry, this is a bounded map. Sorry, the bounded surjection, sorry, that's right. The surjection is the restriction map. So the fact that we have for every element in H check, we can produce an element in D max, and the fact that the restriction from DOM D max lands us in this space means that this space has to be H check of D. Right? So you're right. So this is not a, I didn't mean to say that this is a bounded surjection. This is a bounded map, which gives us that the restriction map is a bounded surjection. Is that clear? Yes. That's right, and the point here is that we really, so what have we done here? So the main thing here is that we have topologized, right? We have fully understood boundary value problems for the D operator, right? So H check of D, we now completely understand in terms of H check of A D naught, right? So we have described all possible boundary conditions from the boundary alone. I mean, of course, this is a slight lie, because the operator A contains some information about the operator D, but it's not unique information about the operator D. You can have lots and lots of operators which have the same adapted boundary operator. And I'm really able to describe the H-check space of these operators with respect to another operator. So in some sense, choosing a good A to understand your boundary value problems gives you a lot of freedom, right? This is saying fix some adapted operator to the boundary, and you can make a choice on that, right, as to what you want. And now with that choice, you can understand all possible boundary conditions. So it gives you a huge amount of flexibility in trying to actually do boundary value problems. Okay, so that's really the full extent of this theorem, right? And it realizes what we wanted before. I don't think you can. So the question is, if you have an operator, a differential operator, can you multiply it so that you can turn it into a bisectorial operator? I don't think that's possible for the simple reason. Suppose you take one of these bisectorial boundary adapted operators, and then, well, it's not just the bounds, but you can sort of introduce spectrum on the entire complex plane. So suppose you take a bisectorial operator, not a self-adjoint operator, a proper bisectorial operator, and then if you rotate the operator now by multiplying by appropriate complex numbers, and you take the tuple of these operators, so in a larger space, now you can produce a differential operator that has spectrum everywhere. Yeah, so here the spectrum will not be empty, right? The spectrum will not be empty because if you take some operator A... Yeah, sorry, so the spectrum won't be everywhere, because if I take this operator A and I do this construction that I just said, then I would still end up with, I mean, it'll be finite copies of A acting on a finite sum of your L2 scales, and then you'll end up with an operator which only has point spectrum, actually. So you'll have point spectrum, but this point spectrum won't be contained in a sector now. So I don't think it's possible to do that. Yeah. Okay, so let's just end the lecture today with just one last and very important theorem or proposition, and we'll talk about regularity next time and move on to boundary conditions. So let U in DOM D max and V in DOM D max bar. Sorry, dagger. Then, given any adapted boundary operator A that is omega bisectorial and invertible, what do we have? We have D max of U V L2 on MF minus U D dagger max V L2 ME is equal to negative U restricted to M V restricted to M multiplied by this endo. And what is this pairing, this is H check A of D naught cross H hat A of D naught. Okay. So, by density, it suffices to consider u, v in C infinity C, u in C infinity C, m e. So when I say, I should say by completeness. Let me just be really explicit here, so that by completeness of D and D dagger, it suffices to consider U in here and V in C infinity C MF. Okay. So then by Green's formula, what do we have? We have D max, or D of UV minus U of D dagger V is equal to U restricted to M, negative sign here, sigma naught star V restricted to M L2 on the boundary. Okay? So now, choosing eta as before, in theorem, what do we have? We have that eta of u is in dom d cl, which is equal to dom d naught cl, which is contained in dom d max, and eta of v is contained in dom d dagger cl, cl equals dom d dagger naught cl, which is contained in dom, there's a 0 here, 0 max, and this is a d dagger 0 max. Good. So moreover, eta of u restricted to the boundary is equal to u restricted to the boundary, and eta of v restricted to the boundary is v restricted to the boundary. So by previous proposition, we have that u restricted to partial m. We already have an integration by parts formula for d naught max and d naught dagger max, right? We already proved that. So now we just apply it to there, and we know that we can now express this L2 integral precisely as we want it, right? I mean, this is also something we should expect. So, I mean, with a lot of these boundary value problems, the problem of understanding, you know, boundary conditions and so on and so forth is really a question close to the boundary. So it doesn't really matter what happens far away. Okay, so maybe I will leave the lecture there for today rather than starting on the new, on something new. From next time, we will look at regularity up to the boundary for these general operators D. And then we'll also move on to talking about things like index theory and so on and so forth. Thank you. Are there any questions? Okay, so see you next time.